So today I am going to tell you few techniques what we use for solving DC circuits. They are very common techniques and most of it you would be knowing, but just to revise, what is very commonly used in most of the entrance exams, wherein you won't be required to use the Kirchhoff law at all. Most of the entrance exam questions and almost all the questions which have come in IIT JEE, never ever was the Kirchhoff law required to be used. By using this technique, you can avoid using Kirchhoff law. Some of the techniques, in fact, are derived through Kirchhoff law itself. So, say the first one is equipotential points in a circuit. You can connect them or you can disconnect them. That means join or disjoin equipotential points in a circuit. Now, if joining makes the circuit look simpler, you can join them. If disjoining makes it look simpler, you can disjoin them. One of the say common problem would be like this, where you can use. Suppose you have to find the resistance between these 2 points, point A and point B, which are two adjacent edges in a cube. Any one side, 2 points on that side, what is the resistance between them? So, first is, which you will be using always, is first to see the symmetry of the circuit, whether the circuit is symmetric or not. We find that such circuits are having a lot of symmetry in it. This current from here can go to be either this way or through this and this. This path, the yellow path, this one, and this path is exactly the same. The current goes like this, it has two choices, and then like this and to B. Again it has two choices. Here same, it is going through a square path, part of a square. This also has a squarish path with the choices when it has. So this current is exactly equal to that current, which is not equal to this current because this path is not as this path looks like. Okay. So this path you can't just by seeing the circuit say that it's the same current. So the orange current is something else. Now symmetry of the circuit, by symmetry of the circuit we can say one more thing, that if this was say yellow was I, then this is again I current and this one is say capital I. So two small i's plus one capital I is going. One capital I comes back to B. Two small i's have to come back to B. Since the circuit is symmetric, it will come exactly the same way. This will have I in it and that will have I in it. Okay. So, if the current in this resistance, all resistances are same. If the current in this resistance is I and the resistance is R, how much is the potential drop? It's IR. What is the potential drop across this point? It is again IR, because I current, same I current and same R resistance. Since the potential drop across this point and this point is same, we can say the potential of this point and potential of this point is same. Because this point potential as such is same because it's the same point. So suppose the potential over here was VA. This would be VA minus IR and this would be again VA minus IR. That means these 2 points are the same points. Electrically they are the same points. You can join them, you can put this point over that point, the circuit will not change. You can put a wire between them, no current will flow in the wire. Why no current will flow in the wire? Because there is no potential difference between these 2 points. Similarly, I current was coming from here and I current was coming from there. And the potential over here becomes VB. That means this potential must be VB plus IR. That minus IR gives you VB. Here also it would be VB plus IR. Both the points would be again same points. So this is 1, and this is 2 and 2. And out. So these you can join, and you can if you are able to find, you can find more equipotential points, but joining this and this will make the circuit very easy and we can solve it. Like if I join these two, the circuit will look like this. This was your A, there is a resistance, and then there is your B. There is a wire like this, having a resistance, you come to point 1, there is a wire like that, having a resistance, you come to point 2, and 1 and 2 is joined. The front square I have drawn basically. 1 and 2 is joined. So I have covered this resistance, I have covered this, I have covered this, I have covered that. Now this again 1, point number 1 again. So this 1, there is a resistance between A and point number 1, which is this one. I will make that point again over here, and this resistance becomes this resistance. This resistance is that resistance. This resistance is covered now. Similarly, this resistance which goes to point number 2, from B to 2. From B to 2 there is one resistance, from B to 2 there is another resistance. Two resistance from B to 2. I have drawn one from B to 2, the other one I will draw. This is again going from B to 2. Okay, so this we reach. Now call this point as say 3, call this point as 4. I will make a point 3, I will make a point 4. Now from 1 to 3 there is one resistance, and from 1 to 3 there is another resistance. So there are two resistances from 1 to 3. So I will draw both the resistances. One is this and the other one is this. Similarly from 2 to 4 there is two resistances. So this and this. So you have covered 2 to 4, 2 to 4. Okay. 3 and 4 is joined by one resistance. So 3 and 4 is joined by one resistance. 1 to 2. This resistance we have not drawn yet. So from 1 to 2 there is one more resistance. This was 1 to 2, one resistance drawn. 1 to 2, one resistance. 1 to 2 there is one more resistance. So 1 to 2 there is one more resistance. We will draw that. And now you can see there were 12 resistances over here. On the 12 edges of the cube, we have 12 resistances over there also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this circuit you can see is very easy to solve, and you can solve it anyhow. This 2 will become 1 R by 2. This will become another R by 2. These three will be in series. So this totally will become R plus R by 2, and R by 2 is 2R. This 2R and this R by 2, R by 2 over here is in parallel. So 2R, R and R in parallel, or 2R and R by 2 in parallel. So you will get 1 by 2R plus 2 by 2R plus 2 by 2R, which is equal to 2R by 5. So this 3 will give you 2R by 5. And hence your circuit will become 2R by 5 over there. These two together is a single R by 2, and this two together is R by 2. So these three are in series, so you will have 2R by 5 plus R by 2 plus R by 2. This is R, these two are R itself, so it is 5 plus 2, 7R by 5. So these three in series will make a resistance of 7R by 5. Now 7R by 5 in parallel with R will give you 5 by 7R plus 7 by 7R, which is 7R by 12. So that will be the resistance between A and B. So what we have used over here is the equipotential points you can join. When you are joining the equipotential point, the circuit is becoming quite easy to solve. And also what we have used is the symmetry of the circuit to distribute the current. Now you may disjoin also, you may join also, like say in a Wheatstone bridge. Suppose there is a situation, 2 by 6 is equal to 3 by 9, I am not going to do the Wheatstone bridge again. Hence we know that no current is going to flow over here, because this potential is equal to that potential. The ratio of the currents would be in this ratio, 3:2. Here it will be say 2I, here it will be 3I, such that the drop is same. The current in this is 3I and the current in this is 2I. The potential drop is same. Now these 2 points are having the same potential because it's a Wheatstone bridge. Hence either you join it and make this circuit as this circuit 2, 3, 6, 9. This circuit is same as this circuit because you can make a long wire short and it will look like this. Or you can disjoin it also. In both the ways, you will get the same answer. 2 and 3 in parallel is 6 by 5 plus 6 and 9 in parallel is equal to 3 times 6 by 5, 18 by. So you'll get 6 by 5 plus 18 by 5, which is equal to 24 by 5. If you do like this, you have 8 and you have 12. 8 into 12 divided by 8 plus 12, which is 20. So again you cancel with 4 and you have 2 times this is 24 by 5. Anyways you do. So we are seeing that you can disjoin a equipotential point or you can join a equipotential point and the diagram remains, the circuit remains the same. Another concept which is very often used in IIT problems, I think it has come most of the time in IIT problems, is if a branch is contributing no current to a joining branch, you may disjoin the branches. That means, let us see an example. Again I am drawing a very common circuit. You can get any circuit on these concepts. So if you have to find the resistance between A and B, we can very well see that it is again very much symmetric. If the current I1 goes over here and I2 goes over there, the total current which has to reach back will be I1 plus I2 and will be in the same way, I1 and I2, because of the symmetry. If you reverse the circuit, they will go the same way, and they are symmetric circuits. So if I1 was going from here and I1 is coming back from this branch, it tells me that this current wholly goes into that, and we can assume that no current is being contributed from this branch into this. So whatever current is coming in here goes back to there. Hence this point you can disjoin. If you disjoin, the circuit looks like this. If the circuit looks like this, now it is very easy to solve. 2 and 2, 4, which is in parallel with 3, and then these will be in series. These two are in series, which are in then parallel. So this kind of question, wherein you'll have to see whether a current is contributing to the other branch or not, is a very common type. Even if it is joined over here, and suppose due to the symmetry of the circuit, this total current goes over that side, and then this current, the orange current, goes to this side. This, even though they were joined, you can disjoin them. You can disjoin them and solve the circuit more easily. Okay? If it reduces the circuit, you can do that. This one is particularly common in IIT questions. Now the next technique is the one, this is going to make your calculations very fast. If you are using it properly, and if you have an eye to see where it can be applied, you can apply it in a lot of places and you can make your calculations really fast. Say, it is using the fact that batteries in parallel is equivalent to, with the internal resistance is equivalent to a battery of EMF R and internal resistance R, where this is given by E1 by R1 plus E2 by R2 plus dot dot dot, where 1 by R is equal to 1 by R1 plus 1 by R2 plus dot dot dot. This we are going to use in a lot of places to make the circuit look short. I'll just show you an example and try to use it wherever it comes. It will make your calculations fast. Suppose there is a battery 6 volt. Okay, let the resistance be say 4, 3, 2, 4, whatever. So suppose we have to find the current in this branch or this branch or this branch. We have to solve it. We can solve it in many ways. You can use Kirchhoff's law and all, but I have shown a very small circuit. You can use it in bigger circuits. What we can say is this battery is in parallel to that battery, and hence they are together as one battery. So this will become a circuit of, assuming this to be positive, a battery with some internal resistance, and this resistance remains where it is. This and this we have combined together, saying that 2 plus 4 was the internal resistance of this battery and 4 is the internal resistance of that battery. Whether it is or not internal doesn't matter, because the formula is coming from the Kirchhoff law and it has to be correct. So E of the equivalent battery becomes, first we will find the R. Small r would be 1 by R is equal to 1 by, this is 6 plus 1 by 4. So it is 2 by 12 plus 3 by 12, hence R is equal to 12 divided by 5. So we have this as 12 by 5, and the EMF of the battery will be given by E upon 12 by 5 is equal to, E1 is 6, since we have taken this as plus and this is also in the same direction, same polarity, upper one is plus, so 6 plus 6 divided by the internal resistance of this, which is 6, and this one is in opposite polarity, so we will take it as minus. Suppose our answer comes as minus, that means this battery is ulta in direction. So this is 4 divided by 4. So what we get over here is E is equal to 1 minus 1, and it is coming as 0 in this case. EMF is 0 in this case, hence no current is going over there. We could have also done using that these three batteries, this and this, I am calling this a battery with the internal resistance 3, a battery of EMF 0. If there was a battery of suppose EMF 0.001, you could have applied the formula or not. So all three are parallel, and we can again use the formula, and this circuit, the whole thing becomes a single battery and a single resistance of value E and R, wherein the circuit is open now. It is not closing with anything. This all three and this, these are the 2 points, which is this point and this point. This is the equivalent open circuit. Open circuit, so we will get the voltage across this, and hence we can find the current. Anyways, let us see using that and this whether the answer is same or not. This tells you that there will be no current in here, 0 current in there, because equivalent is 0. Hence the circuit becomes, there is no current, you can rub it off, and then this will be the circuit where this battery will be in series with that battery, and you can see that plus minus is going to plus and this is minus. So these two batteries are in series and becomes a 10 volt battery, and the total resistance is 2 plus 4, 6 plus 4, 10. So 10 is the total resistance also, 10 is the voltage of the battery, hence 1 ampere is coming out. 1 ampere goes like this according to that solution. 1 ampere goes like this, 1 ampere, 1 ampere, 1 ampere, 1 ampere. If we just see the potential difference across these 2 points, it must be 0. 1 ampere is going. Let us see, say some potential X. X plus V is the potential over here, and this is along the current, so minus IR, minus 1 into 4. So plus 4 minus 4, this is 0 potential across this point. So this is again X. Similarly over here also it is minus 4 plus 6 minus 2, which is 0. Hence no current is going in that. Now let us see that all three as a battery if we take, then what is the new R? The R would be, this R would be 1 by R is equal to 1 by 6, 2 plus 4, 6 plus 1 by 3 plus 1 by 4. This is all plus plus plus, whether the battery is in the same polarity or the opposite. So R is 12 by 9. 12 by 9 or 4 by 3 is your R. Okay, it was actually not required in this because eventually you are going to get a zero potential battery again. So what is the E? E will be equal to E by R, which is 4, 3 will be equal to E1, which is 6 by 6 plus E2, which is 0 by 3 minus 4 by 4. Again it is 0, so this is a 0 volt battery anyhow. This tells you that this is a 0 volt battery, so this potential is 0. Suppose it came out to be a 3 volt battery, then this potential will be 3 because no current will be flowing across this assumed resistance. This is not an actual resistance in the circuit, hence no current will be flowing, and this potential difference would be 3 volt itself. So this potential you are getting as 0 in this case, and again you can solve the whole circuit because this potential is 0, you can remove the branch and solve the circuit. Unfortunately I took values which is giving 0 volt battery, and you are not able to see further on how you can proceed this way. But if you have to do more problems on this, there is another video which is based on solving circuit only using by this method number 3. You can watch that video. The next one is, okay, before going on to the next circuit, one very simple point, you should be on the lookout of this also. Suppose you have a resistance like this. Okay, I'll draw another common circuit. It's quite common. Now you have to find the resistance between this point A and B. First of all, you should see which is the shortest path of going from A to B. If I go like this, I involve 3 resistances. If I go like this, I involve 2 resistances. Say all are R, then 2R. If I go like this, again it is 2R. If I take some other path, I can make a round also, it will just increase the number of R. It can't go that way, but I can choose any path. So the shortest path I see is a 2R. Your answer, your final answer has to be less than 2R no matter what. Why? Because one path is of 2R, any other path is an alternate path, it is like a parallel path to that. If you have alternative paths to any short path, you have your resistance less than the shortest resistance, the least resistance. So you should be on the lookout of the shortest path so that when you get to your final answer, you can at least see that it is less than the shortest possible way or not. Like the first question of this one, this cube wala question. Here the shortest path was 1R resistance path itself. Your answer has to be less than 1R. I think it came out to be 7 by 12R or something. It has to be less than 1R. Okay, now we'll go on to the capacitance. Circuits involving capacitance. So you have to have a clear idea that if you have a capacitor in a circuit, first of all, the current, the source which is charging the capacitor, the current has to go through a resistance. If there is no resistance in the path, the capacitor will get charged instantaneously. Then you don't have a charging and discharging formula for that. It charges instantaneously if there is no resistance. Now first, before starting this, again the capacitance video is there separately, but you should understand few physical things about capacitance, how it is actually behaving, and if you imagine it properly, you will be able to solve it very fast. A capacitor is, I would say, it is equivalent to a spring in a mechanical system. Now, if you put charge on the capacitor, it is like a stretch string. If you put plus Q charge, it is same as you have stretched it and there is energy stored in it as potential energy, as a spring energy over there. And suppose you have a battery, V volt battery. When you start charging, the current is as if this resistance is 0, it will be fully V by R will be the initial current, and when it is fully charged there will be no current. This potential difference will be same as that potential difference, that you know. Now battery in a circuit is same as you have put a say load on the spring or a constant force on the spring. If there is a constant force, then what will happen? The spring will slowly go. This is not a sudden load, and it will not do SHM over here. We have questions of SHM, but in DC circuit techniques we are not doing the SHM part. There is a constant force which is going to extend the spring to a certain level where your Kx is equal to F. So here also, and then it will get stabilized. Here also, if you have put a voltage V, it is same as putting a constant force, and first it was balanced at 0 charge, now it will be balanced at some other charge. Say this capacitor has a value of 1 units, and this voltage is 6 volt, and this resistance is 2. Okay, the final voltage on this has to be equal to 6 volt. The total charge on this will be equal to 6 units. The total charge will be equal to 6 coulomb. So Q is equal to C into V. Now this 6 is same as it has stretched, the spring has stretched 6 centimeters and again come to rest. Now whether you had started charging from initially the charge on this capacitor was 3 coulomb or the charge on this capacitor was say 7 coulomb, doesn't matter. Finally it will rest at 6. It is same as saying you have stretched the spring 3 centimeters and you have put a force as that 6 into K into 6 is equal to that force, then it is going to settle at 6. If you stretch the string more, it will go back and settle at 6. Hence, whether you put 7, 8, 10 or 6 coulomb charge, it is going to settle at 6. So meaning to say, if you put 2 coulomb charge on this initially, capacitance is 1, charge is 2 coulombs. Okay. Now it is going to charge from 2 to 6. Initially it is going to approach, there is a difference what it wants to go to. It wants to go to 6 coulomb charge, is 2 coulomb charge, it will go very fast, but as it approaches 6 it will charge very slowly and approach 6 in infinite time. Similarly, if the initial charge was say 12 coulomb, it is like the spring is stretched too much, it is going to go back to your 6. Initially it is going to go very fast, but as it approaches 6 again it will slow down. So it is same as your damped oscillation. Like this one, force mg is acting and it wants to settle down here. It will go and settle down here, but it will go very slowly. Initially it will have a movement, but it will slow down as your damping equation, and it will stop over there when it reaches the required height. So if you notice your damping equation in your NCERT books, it has got the same factor e power minus t by tau in those equations also. So so this is the basic of capacitors. So if your question is coming, first you have to imagine how it is going to behave. So first thing in a capacitor circuit, you have to see what is the final charge it is going to go at. Suppose I make a circuit like this. This is your E, is the resistance R, say another R1, R2, R3. Since there is a resistance which is charging the capacitor, it will go and charge slowly. Suppose these two resistances were missing, this will charge instantaneously. Now if I have to solve this circuit, first of all I have to see that finally how much will be the charge on that capacitor. So final charge, let us assume some value, say this is 6 volts, say this is 2 ohms, this is 1 ohm, and this is again 1 ohm, say. Okay, so obviously when it charges fully, this part is out of the circuit. The total resistance is 2 plus 1, 3, and the current flowing in this is at that time when it is fully charged, I final will be equal to 6 divided by 2 plus 1, which is 6 by 2 plus 1, which is equal to 2 ampere. So 2 ampere will be flowing, 2 ampere will be going down, nothing will be going in there, and 2 ampere will be returning. So the potential across this point is 2 into 1. The potential drop across this point is 2 into 1, which is 2 volts. So this will be charged to 2 volts. The capacitor will also have 2 volts on this. Let the capacitance of the capacitor be C is equal to 1 farad. Okay. So the charge required on the capacitor would be equal to Q is equal to C into V. It will be 1 into 2, which is 2 coulombs will be the charge on the capacitor finally. So from 0 it is wanting to go to 2 if it started charging from 0. And if you have to find that at any time what is the charge on that capacitor, you can do it in many ways, but since we were talking of this, we will try to do it this way. This circuit, okay, such questions you know. So I'll say that the initial charge on this capacitor was, say, the initial charge on this capacitor was plus 8 coulomb this side and minus 8 coulomb that side. I have to find at any time t what is the charge on the capacitor. So first of all, you will see that what it wants to reach to. Finally, when the circuit is, when it is no more charging, it is fully charged, this is out of the circuit, we have found out that this potential difference will be 2 volts according to 2 ampere current flowing over here. Hence the potential difference will be 2 volts. So potential V will be 2 volts. So finally the capacitor would be at 2 coulomb plus over there and minus 2 coulomb on this plate. This will be the final situation. Now this circuit is obviously equivalent to, first of all, the whole circuit is equivalent to that circuit. Why? We can always make this as a single battery. When we make this part as a single battery and a single resistance, there is a 6 volt battery with 2 ohm internal resistance and a 0 volt battery with 1 ohm internal resistance. So 1 by R is equal to 1 by 2 plus 1 by 1. Hence it is 2 by 2. So R is equal to 2 by 3. And this the EMF of the battery E by R, which is 2 by 3, is equal to 6 by 2 plus 0 by 1. So this is 3 and that 3 cancels with 3, so E is equal to 2. So this is equivalent to a 2 volt battery over here, which is obviously true because we will see that if it is a 2 volt battery, then only it stops at 2 coulomb final charge. So you do it anyways, you will get the same thing. So it's a 2 volt battery and this internal resistance is coming out to be 2 by 3. So this total resistance will be 1 plus the internal resistance of this battery and the internal resistance. So that will be in series. 1 plus 2 by 3 is 3 by 3. So it is 5 by 3 ohms. So this is a circuit what you have to solve. Now, and the initial charge was plus 8 coulombs. So we'll see that what is it as a spring. As a spring, initially this is unstretched position of the spring. It wants to reach a stretch 2 charge, 2 coulombs, because there is a battery of 2. It wants to reach that, but initially the spring was stretched to plus 8 coulombs. So it will rush from here to there, and initially it will start discharging very fast, and then slowly it will reach over there. All formula, this is a discharging happening over here, whether the charging is happening or discharging is happening. What is the formula? The formula what you are going to use is this formula is for charging as well as discharging. Forget about the formula VQ is equal to Q1 minus e power minus t by tau. This formula is actually useless because this formula is only when you are charging from 0. If the initial charge was 0, and very few questions you will get actually in IIT where the initial charge was 0. You may get it, but this is the general formula where you can use, which you can use always. So first of all, what is this delta Q? Delta Q is the difference from its initial condition to its final condition. So that is 6 coulombs over here. Yeah, RC is in the equivalent circuit like this. What is the R? Through how much of resistance is it getting charged? So that you have done already. So you can write 5 by 3. C is 1 itself. And this delta Q is if you are at a certain position at any time t. This is t is equal to infinity and this is t is equal to 0. At any time t you are over here, so this delta Q is how much of charge is remaining from the position you want to reach. How much is the charge on the capacitor and where it wants to reach, this is the difference. This delta Q is equal to capital delta Q at time t is equal to 0. At time t is equal to 0, delta Q is equal to delta Q. At time progresses, this delta Q is 6 into a fraction. There is always a fraction, e power minus t by something. So this is what you are going to use always to find. So your answer is say 4. When it reaches 4. The question was at what time it reaches, at what time t is equal to how much, when Q on that capacitor is equal to say 4 coulomb. Then 4 minus 2 is your 2 is equal to 6 into e power minus 3t by 5. This will give your answer. So this is quite short if you do it like this. This is actually what is happening. You should be doing it like this because this gives you the actual picture of what is happening. Suppose the initial charge was minus 8 coulomb over here and plus 8 coulomb over there. No matter what, it will try to reach to plus 2 and minus 2. So you will make it like this. It wants to reach to plus 2. This is the unstressed position. Q is equal to 0, no charge on it, and it is initially compressed to a minus 8. So from here to there it wants to reach. So how much is the pull? The pull is of 8 plus 2, which is 10. So your delta Q will be 10 over here into e power minus t by tau. And if you have reached over here, you want to reach over there, the charge on this is at any time t, the charge is Q. You will write this is Q charge on it, this is minus Q in fact over here, and then plus. So if they ask you when is it plus Q over there, if they ask you plus Q, when is it plus Q over there, you will say now this much is the distance it wants to cover more, this much is the remaining distance. So it is 2 minus Q is your delta Q. 2 minus Q is the remaining distance. If it was minus Q over here, say minus 3 volt. So how much is the distance? Q over here and plus 2 over here there. So this distance is equal to Q plus 2. 2 plus Q. 2 minus of minus Q gives you plus Q also. Is equal to 10 into e power minus t by tau. So this way you can solve large circuits without any problem. Now if you have two capacitors in the circuit, now whether it is charging or discharging, whether you have a battery or not, it hardly makes a difference. We'll solve it the same way. I'm not making a big mesh over here with a lot of resistance in parallel and series on a battery, because eventually you can make it into one battery and one internal resistance most of the time. Okay. So suppose you have two capacitors C1 and C2 and they are already charged to a certain value. Let us assume values. V is equal to 6 volt over here, and there is a 1 farad capacitor and there is a 2 farad capacitor, and the charges on this is, say it is plus 10, minus 10, and this was plus 4 and minus I'll take some other value. It was plus say 2 and minus 2 charge already on it. Okay, and let us assume this is plus and this is minus. So this was the initial condition. Again we have to find what it finally would be, and then we have to make the charging and discharging equation. So it is not like this was 0 charge and that was 0 charge, and simply you can do the equivalent capacitance of this. You can do the equivalent capacitance of this. You can make the two capacitors as a single capacitor with the equivalent charge on it, how much the charge was on it, equivalent to that, and how much it wants to reach. So what is basically going to happen is this minus 10 plus 2, there is a minus 8 coulomb trapped over here. That will go nowhere. That minus 8 has to be over there. So this will and that will redistribute, some charge will go from here to there or there to here, and it will redistribute in such a way that minus 8 has to be over here, and the total voltage across this voltage drop has to be 6 volt. So you can solve it in many ways, and but we'll solve it the way I am showing you right now, and later we'll discuss other ways also. So first of all, this as a physical situation, what is it? Is it right now? Right now, what is the voltage across this? The voltage across this is 10 by 1, which is 10 volt. 10 volt is the voltage across this. And this voltage is 2 volt. This plus 2 plus 10, the total voltage is 12 volt. Plus and minus. And it wants to reach a plus 6 over there and minus 6 over there. That is the voltage it wants to reach. So this situation is something like this. Even if the battery was not there, is it balanced? It is not balanced. Even if the battery is not there. Suppose I tell you the question is without the battery. Some charge is going to go over from here to there such that this voltage drop is equal to that voltage drop, and whatever charge goes from here has to go on that, and inside the charge has to remain totally minus 8. So you will redistribute the charges and see the voltage of this, voltage is the Q by C of this will be equal to Q by C of that. So that way you can solve it. What is physically happening over here is, these two capacitors are like two strings. They have different voltages on it. So they have stretched to different forces. It has been stretched, the voltage is same as the force. This is 10 Newton force and that is pulling with 2 Newton force. So what will happen is, this will stretch more, that means charge will come on this such that the forces balance. When the forces balance, it will be at some new position, but it will be still extended. They will have their extension x1 and x2, which will be the charges on this later on. There, it will not come to the mean position. It will not be like both are unextended. They won't be like unextended. If both the capacitors were of the same capacity and they had the same charges on it, this internally it was 0, if this plus this was 0, then they will go to unextended position. If they were of the same capacitance and inside the trapped charge was 0, then only when this voltage drop becomes equal to that voltage drop, this will be 0, 0, that will be 0, 0, and they will be right in the middle where there is no extension among them. But it is not happening over here. It will come to a mean position wherein this will be stretched and that will be also stretched. Now final charges we can find out directly also by saying that inside total will be always minus 8. Some Q goes over from this side to that side, and this becomes minus 2 plus Q, and this side becomes 10 minus Q. And the negative of that is here and the negative of this over there. inside the trap charge remains minus 8. This is minus 10 plus q over here, and this is plus 2 minus q over there, hence it is minus 8 inside. Now in this condition, the current has stopped flowing, hence this voltage across this should be voltage of the battery. So voltage, say this voltage across this capacitor is, assuming this to be plus and this to be minus, again this to be plus and this to be minus, the voltage across this is minus 2 plus q by C of this, which is 2, plus this you have assumed plus, here the charge is q minus 10 this side, that is q minus 10 by 1. See carefully, I have assumed this plate to be plus, then only I can add this voltage, and that voltage will be the total voltage across this. If I assume this plate to be plus and this plate to be minus, I will have to subtract this voltage minus this voltage, and if I add this voltage, I will take this as plus and this as minus. This plate has a charge of q minus 10, so I will take this as a positive number q minus 10, and this is the negative number, and it should be written as minus q of q minus 10. So this total voltage is equal to whatever was the voltage given, 6 volt, so it is equal to 6 volt over here. So you solve it, you will get minus 2 plus q plus 2q minus 20 is equal to. Now if you have to solve that at what time how much charge is on this capacitor or on that capacitor, or what is the flow of charge, or at any time what is the current in the circuit and at any time t, then you can make the circuit as a single capacitor of value C dash, which is equal to C1 C2 upon C1 plus C2, it is 1 into 2 by 3 in this case farad. Resistance remains same 2 ohm, and there is a battery which is same 6 volt, and this charge is the equivalent charge you will have to write, which is not actually there on any of the capacitor at this time. This equivalent charge would be equal to initial charge. The initial charge would be equal to, say, q initial will be given by what is the voltage difference across these 2 points. The voltage across this is 10 and the voltage across this is 1. So total voltage is 11. Across the 2 capacitors, this is plus minus, there is a 11 volt potential difference across the 2 capacitors. So initially if I consider both the capacitors as one capacitor, again the voltage difference across the single capacitor of C dash value has to be again 11 volts. So if this is 11 volt, the charge accordingly on that capacitor will be equal to C into V. So the charge on the capacitor will be 11 into C, which is 2 by 3, so it is 22 by 3. So charge on the capacitor, what we are seeing is 22 by 3 initially on the capacitor, which is plus 22 by 3 and minus 22 by 3. Now finally this charge will be such that the voltage difference is plus 6 over here and minus 6 here. Right now the voltage is plus 11 over here and minus 11 over there. So it will go according to, again we will draw the line diagram of this capacitor. This capacitor had a 0 stretch, Q is equal to 0 at the, say, this point. It is now at plus 22 by 3, and it wants to achieve, the final thing what it wants to achieve is the minus over here and a plus over there. So you can say that this plate is at say minus 22 by 3 and it wants to achieve a plus value. Plus how much value? Such that the voltage is that. So 6 is the voltage. So Q is equal to C into V. So C is, for this is 2 by 3, and voltage of this will be equal to the voltage of this battery, which is 6. So it will be 4. 4 coulombs. So finally it wants plus 4 coulomb over here and minus 4 coulomb over here. So from minus 22 by 3 it wants to go to plus 4. So the stretch in the capacitor, the stretch in the spring which is pulling it to this position, which is the mean position for the system, is this much is the stretch. So that is what is pulling it. So your delta Q is going to be this big delta Q, which is 22 by 3 plus 4. It is 4 minus 22 by 3, or you can do a difference between this and mod of that. So it is 22 by 3 plus 4, which is 34 by 3. 34 by 3 is your delta Q. E power minus T by RC. R is 2 and C you will take it as 2 by 3 into 2 by 3. Your Q at any time is, say, always take it on the plus side if you have considered this as plus. So say this is Q. So how much is remaining? The stretch remaining is Q minus this value will be less and this value will be more. So it will be 4 minus Q. See, you should write the positive values. This 4 is higher, this Q is near to 0. So 4 minus Q is that value. So this is your Q at any time. If you differentiate this, you will get your current at any time. So this 4 is insignificant, you differentiate this and you will get the current as, this will come in front, 34 by 3 into 3 by 4 e power minus t by tau. So this is how you will solve the circuit. Now this charge Q doesn't give you the actual charge on the capacitor. Suppose you get Q at any time is this, then what is the Q on this capacitor or the Q on that capacitor? That this Q at any time T on this equivalent capacitor is given by 4 minus 34 by 3 e power minus t by RC 3t by 4. Then the voltage difference across this capacitor V is equal to 4 minus 34 by 3 e power minus 3t by 4 divided by Q by C, the capacitance of this, 2 into 3. This is the voltage. This should be the voltage difference across this plus that. So say Q charge is remaining on this. You wanted how much is the charge on this one, and this we have achieved where plus Q is there. So assume that this is your plus say capital Q. So the voltage across that one is plus capital Q by 2. If this is plus capital Q, you can see the total charge outside has to be 8 plus 10 minus 2. So I have put a plus Q over here, so this will be 8 minus Q, so that the total charge outside is 8 and total charge towards inside is minus 8. So it is, this one is 8 minus Q, this plate. So I can write this plate as Q minus 8. Voltage drop across this is Q by 2 and voltage drop across this is plus Q minus 8 by C for this was 1. So you can see that I have taken this plate as to be positive and I have written Q minus 8 and this plate to be negative and minus of Q minus 8. It's your wish, whichever way you write, and this is plus minus plus minus, so total voltage difference is this plus that. So this is the way I have written it. It becomes this 2 cancels with this is 3Q. These are charging as well as discharging. I am not even seeing whether the charge is increasing or decreasing. This is what is happening. You have to use the same formula for charging as well as discharging. In fact, when you use this, Q is equal to Q 1 minus e power minus t by tau. If you open the bracket, this is Q minus Q goes over there and that Q e power minus t by tau comes over here. In that unstressed thing, I always had Q is equal to 0, unstressed position. Initial position is also this. For the capacitor which is going to charge, initial position is also this. And finally it wants to charge to say plus Q. Then how much is the delta Q? Delta Q is Q itself. Okay. And after a certain time it charges to a value of say Q. Then how far it is remaining from the position it wants to attain? This is the mean position it wants to attain. And how far is it still to go? It is Q minus Q. This is your delta Q over there, small delta Q. Capital delta Q is the initial stretch from its initial position to the final position it wants to go. Whether both are positive, negative, both are negative, you have to see the distance between them. And small delta Q is at any time when it is at a certain position Q, still how much distance is remaining to go to reach the equilibrium position, the mean position. So still this much is remaining to go. That is delta Q at any time t. So this is the equation. This equation you see is only when it starts at 0 charge. Suppose it started at minus 2 charge or minus Q dash charge, where Q dash is a positive value. So your delta Q would have been, this part would have been plus Q plus this much length. This is the initial stretch. That stretch will dictate how fast it will go. And when it reaches a certain position Q, you can rewrite this thing, Q minus Q. Similarly, if I have to show you the discharging one without any battery, it is already having say plus Q charge. Then it wants to reach 0 finally, and initially it is at plus Q. So how much is the stretch? Plus Q is the stretch. E power minus t by tau is equal to, at any time it reaches say Q, then how much is the distance remaining to reach the equilibrium position? This is the equilibrium mean position, because it wants to become 0 charge. So how much is the distance remaining? That Q, delta Q is equal to Q distance is remaining. So this you get for discharge, but it's the same thing. And they want you to find in how much time this capacitor charges. This is a battery of say E1 and E2. Obviously you can reduce this circuit to again single battery and single resistance. This part will become one battery with a single resistance. So that battery and that resistance will be in series with this and that. Hence these two batteries will become a single battery and a single resistance, and you can do it. If you have capacitor over here like this, C1 and C2, you can make these two capacitors as a single capacitor and solve the question. Again, if they are initially charged, you will have to find the initial condition of the capacitor. As a single capacitor, what is the condition? When you have two capacitors like this, say let me give you a value. Both were discharged, then you can obviously make it a single capacitor and solve the circuit. And when they ask you what is the charge on one of these, you equate the voltages and you can get the charge ratio on the two. Now, if I give you something like this is the capacitor of value 1 farad, and this is the capacitor of value 2 farad, and this had an initial charge 2 coulombs on it, and this also had an initial charge 2 coulombs on it. This was charged by some circuit and this was charged by some other circuit, and then that circuit was removed. When you close this and you put this into operation, this is like this: 1 farad, 2 coulomb, 2 farad, 2 coulomb. They ask you what is the charge on the capacitor after a certain time. First of all, this voltage is not equal to that voltage. This voltage is equal to 2 by 1, and that voltage is 2 by 2, which is 1 volt. Since the voltage is not equal, this is a short circuit over here. Since this is a short circuit, without any charge flowing from here, first of all the charges will interchange and this will become balanced. This voltage will become equal to that voltage, charges will shift instantaneously, and then when the voltages are same, then only you will start charging or discharging. Okay. So see, next part is oscillation. Oscillation is also pretty easy, it's the same thing, but I'll be discussing that. You have an inductor. I'll be discussing this in when we do AC, towards the end of AC. This also you can consider as same as charging discharging circuit, and you can do it. That's it.